Okay, today we're going to talk about work and energy. I've already posted a video from Professor Dave, who's he explains things fairly simply. So I really liked his YouTube video, so I'm not going to reinvent the wheel and double post it. But there are some bits and pieces of some PowerPoints that I want you to reflect on. I'm going to expect you to understand, so I'm going to post this and you need to be able to answer these. Some of these are going to pop up as part of your written um, test for this unit. But energy is kind of a big concept, and understanding how energy can be transferred and where energy exists in life. That's kind of a big hot topic as well. Just the idea of the different types of energy. We're always seeking out new types of energy to support our world. So this is complicated, but I expect you to, and you're going to be in the video.
Oh, cool.
Yeah. So I expect you guys to have some basic understandings of the working of energy. In the Professor Dave video, I'm going to go over, we came across an issue with understanding displacement and force. Um, from one of the questions on the physics classroom. The question regarding a roller coaster, and I'm going to take some time to kind of explain it and kind of post explanations along with Professor Dave, but I also try and explain it in a separate video here as well. So that's something that can be discussed, and hopefully it'll help you understand. It's notes B, question like 3 or 4 on the section B of notes in work and energy. So, okay, step 1, make sure you're working through Canvas. Step 2, this stuff needs to be answered. It can be answered either from the Professor Dave content. You're welcome. I mean, I can't stop you from Googling, but I do expect you to be able to explain stuff in your own words. So make sure whatever you're writing here, makes sense to you and makes sense to me. So these are notes. This is going to just be kind of a completion points. Again, there's going to be a series of questions that you need to work through here. So if you notice, each page just says work, definitions, and then it goes into questions. So all these questions, there are 3 questions for each topic: work and energy, positive work, negative work, 2 forms of mechanical energy, and then sample problems, right, that follow. And then it moves on to kinetic energy. Again, another video from Professor Dave and from my discussions. So you do need to go through this, but this is another situation where, hey, if you don't understand what's going on in this particular question, highlight it, circle it, whatever, and review it with me. Okay, so there's this. I'm going to go through a series of work energy sets of notes. So I really liked, again, I'm a big proponent of not reinventing the wheel. So I found this from somebody else, and I really like this. So usually you can take physics in junior high, and by physics I mean conceptual physics, so which is very base level. And they define it as work is force times distance. But I want you to understand a little more in depth as you are just about graduated seniors. Energy is a conserved substance, so it has the capacity to produce a change in any sort of object, and it can be transferred from one thing to another, and in that transfer it often will change what it looks like or how it acts. So types of energy: you can have stored energy, and here are the ones that you've probably heard of or talked about before. Kinetic energy, which is often referred to as like motion energy, energy in motion. Gravitational energy, the energy of that pull of gravity. Elastic is the bouncing, Energy dissipated is anything that's usually like frictional energy. When you like slide across the floor and you feel that heat, that's your dissipated energy. You've slowed down due to friction. Chemical energy, that could be um, anytime a chemical reaction produces some sort of heat. Nuclear energy, nuclear bombs, just like bouncing off of like electrons and electron particles, atomic bombs, like those sorts of things, and electromagnetic energy. So that's going to be your light rays, that the UV or the UV rays, the Roy G. Biv, the red, orange, yellow, green, blue rainbow spectrum, X-rays, microwaves, that whole spectrum of light, infrared, all of those are also types of energy. Okay. Um, so if this helps, different types of energy can be stored in different ways, and it's like money. They can be saved and kind of come and go as a checking account. It could be a certificate of deposit, which if you're not familiar with that, that's money that gets like put away for 10 years that you don't actually have access to. So that's like this kind of like potential energy. It's like there, and you can use it, but not right away. Um, Money market account. Oh, okay. See, this is where I get rusty on money. An IRA is like in a retirement fund where you kind of store money away and you really can't use it for a long while. So all of these are similar to energy. Like it can be stored in a variety of different ways. Okay. And then it can be transferred. Okay. Just like you can move money from one account to another, you can move energy by doing work. So by applying a force and over a certain amount of distance, by adding heat or releasing heat or expanding that energy. Okay, so I like that first little section here. So the next thing we're going to kind of talk about, we're going to review again. Do this. So I want this swap. Okay. Work. So when we're dealing with just work, it tells us how much force we're applying to something to allow that shift in energy. So how much effort, and this goes back to that savings account or that different types of bank accounts. When you think about like an IRA, if you know what that is, I don't know what it stands for. I'm not a money person, but it relates to your retirement. Um, so if you have a savings account, you can put money in, and you generally can take it out without a lot of penalty. Checking account is even more common. Like you can just use your debit card and just pay for stuff straight out of your checking account. All right. It's almost like I can dump money in a Venmo or a PayPal account and just pay. Same with like Apple Pay. You can just use that money. It's readily available. So that's energy readily available. All right. Some things like a retirement fund, if you start putting money away for retirement, I know you're young and that's not something you necessarily think about, but once you start putting that in that special labeled account, it is really hard to get that money back before a certain point in time. All right. So the work is how much force or how much you have to put in order to get that energy change, in order to get that energy to change hands from one type of energy to another. All right. So work is a bridge between Um, work is the bridge between force and energy. So force is a vector. And I asked this all the way back in the very beginning, and it's really important that you understand the difference between a vector and a scalar. A vector always has a directional component, and this is really important. If you're pushing something, if the work you're doing, the force you're applying is pushing in one direction, but you're pushing a car that's rolling down a hill, you are applying a negative force. You're applying a force upwards while the car is rolling down the hill downwards. So you're working against it, okay? Which would be different if you were behind the car pushing it down the hill, all right? The arrow, the vector quantity matters, okay? Where a scalar is exactly as the name sounds, scale. When you're dealing with a scalar, it can only have a scale. Energy just has a number. You can't like point energy at something. There is just energy. It's just a number, right? Where force is directional. And it's important because the way you apply that force changes the movement of an object or changes the overall number of that energy. Okay? So here's the equation you need to know. Work is force times, this says change in, like, I don't even know what they're looking for. I'm not sure what they're saying. Here, displacement. I've never seen displacement represented by R. But displacement is how much space between point A and point B, the distance between that object, okay? And then cosine theta. Okay, this is going to come up or has already for some of you on that physics classroom assignment. It's the angle between the force and displacement. And what that actually means, like if you're just pulling, like I have my rolly chair, if I'm just like pulling it directly across the floor in a straight line direction, there is no angle between the force and the displacement, okay? Because it's just moving in this direction. When the angle matters is like when you, I'm trying to think. Because that even applies, like if here's this random technique, okay? When I pull up, I'm going in this direction. This is the direction of displacement, and the force is this way. So again, the angle is 0. All right. So now where the angle really matters is when you're like pushing an object at an angle. All right. I really like how in the video that I had you watch before, how Professor Dave explained, like if you're pushing down on a box, like at an angle, so here's your box and you kind of push at an angle, the only force that really like affects the energy transfer, the movement of the box, is the horizontal component, this component. So if you're pushing at this sort of angle and it's moving across the ground, the only thing that matters is the amount of force like going this way. All the force moving, all the vertical component is negated. Like all that energy you're kind of using to push downwards, it's just being lost into the floor. So, so the question I'm referencing in this case is in the physics classroom, they brought up a situation, I'm going to run out of time, a situation where a roller coaster is going up a height of 60 meters. And then they have 3 different angles to get there. All right. That movement of the roller coaster is all in one direction. It's in the same force, the displacement and the force are in the same direction. So the angle doesn't end up mattering. That's not even a word. The angle doesn't matter. So you're just going to use force and displacement, and cosine theta will be 0. Or the angle will be 0. Okay, so I guess we're going to stop there because I rambled too much. Think through that, try that with that first question, and we'll move on from there with the next video.